Hello, Physics 30s. One more lesson. So we are Unit 6, Lesson 7. We're talking about particle classification. And what I mean by one more lesson, this is it. This is our last lesson of Physics 30. Um, I really wish that we were here doing this lesson together and realistically all the other lessons that we missed. But this one is kind of, it's mixed here, mixed emotions, because on the one part I'm excited, you're finished the course, you're ready to move on to bigger and better things, other things. On the other hand, it's a little bit sad because, well, it means that our time together is coming to an end. So I don't know, mixed emotions. We'll just leave it at that. What I do like is this lesson is pretty darn cool. Like there's some neat stuff in here, some things that you may not have heard of a ton of before. We're really starting to explore stuff that you haven't heard much of, at least in the high school side of things, or junior high or elementary for that matter as well. Um, I'm going to give you a little bit of a warning though. Little bit of a warning. We are scratching the surface with this stuff. There is so much more to it. Just like a lot of things that we covered in Physics 30, kind of just scratching the surface. You can dig way deeper into this if you want to, and in particular this lesson, way, way deeper. But anyways, let's jump in here. So using particle accelerators, that's the thing we talked about last lesson. Hundreds of new subatomic particles were discovered. That's no word of a lie. Hundreds of new subatomic particles, or subnuclear particles, I should say. So things that the nucleus is inside of the nucleus. Physicists have organized them in terms of their fundamental forces. And these are some nice squishies, some what are they called, like plush toys or stuffed animal type toys that show us the excuse me, that like you can buy these at Tellus World of Science and stuff like that too. They're like stuffed animals for the different subatomic particles, which is pretty cool. Okay, so if we're organizing them by their forces that they experience, we should probably have an idea of the forces that things can experience. So these are listed in order from strongest to weakest, and we should have an idea of strongest to weakest. So we've got the strong nuclear force, obviously the strongest, then the electromagnetic force, then the weak nuclear force, then the gravitational force as the weakest force of our four fundamental forces. Now these are the four forces that can explain pretty much everything as we know it right now. Could be others out there, who knows, but for now this is what we got. So just to give you kind of an idea, like if I gave the strong nuclear force a strength of 1, my electromagnetic force would be 137 times weaker. My weak nuclear force would be 1,000,000 times weaker. And then my gravitational force, like I don't even know what you would call that, but 6 times 10 to the negative 39 times weaker. So just like bajillions, I'm going to make up a number for it, bajillions times weaker. Cool, and then of course the range that we look at for this, we know that the nuclear strong force is ridiculously small, like a ridiculously short force, only really acts when those nucleons are right next to each other. The electromagnetic forces, infinite. The weak nuclear force, even smaller range, 1% or 0.1%, sorry, of the diameter of a proton. So only really acts inside of nucleons, inside of protons and neutrons. And then the gravitational force extends out forever and ever and ever and ever, and we've talked about that a little bit before. So the major categories of particles that we're about to talk about here, we've got leptons, hadrons, and field particles. Let's jump right in. Leptons are our true elementary particles. That is, they have no size and they have no internal structure. So you can't break them down at all any further as far as we know. No size whatsoever and no internal structure. Now the leptons that we've talked about are electrons and neutrinos. And of course their corresponding antimatter, anti-electrons or positrons, and anti-neutrinos. One thing we want to know about this is they do not experience the strong nuclear force, but they do experience all the other forces. So leptons, no internal structure, simple, 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 and the ones we know about, electrons, neutrinos, and their antiparticles. Hadrons do experience the strong nuclear force and all of the other forces. So they experience all the forces. The ones that we're kind of familiar with, protons, neutrons, and of course their corresponding antiparticles. Turns out the hadrons are kind of the interesting ones. Hundreds of different types of hadrons. Hundreds. We'll talk more about that in a second. Finally, we've got field particles or gauge bosons. These are the quanta or the individual pieces of the forces and fields, and they're the carriers or the mediators of these forces. You could look up some YouTube videos on this if you want to. It is some pretty interesting stuff with these field particles. So the field particle that we are familiar with is a photon. The one that we have talked about so far is a photon. But yeah, check out some YouTube videos. There's some really interesting stuff. I really love Veritasium. Oh, now should have thought of this before. Veritasium and In a Nutshell is pretty good, and Vsauce is really good, and Minute Physics is really good. Anyways, there's a couple. Okay, so particles and antiparticles. So getting into the next little bit here, we kind of already know about antiparticles. Kind of. I mean, we've heard of them in this course before. But an antiparticle is identical to its corresponding particle in every way, shape, and form, except for its opposite charge and some other more advanced properties that we don't really get into in this course. Every known particle has an associated antiparticle. So, electrons, we got positrons. Protons, we have antiprotons. Yep, and the spelling went out the window on that one as I started to look ahead. Neutrons, we have anti-neutrons. Oh boy, neutrons. That's pretty close. I am really having a hard time with my spelling right now. Okay, neutrinos, we have anti-neutrinos. If I slow down, it's a little bit better. And then photons, it's a trap. There is no corresponding photon antiparticle. So photons are, like I've told you before, photons are pretty weird. You should check out some videos on photons too, if you're interested. So we've mentioned this one. We're going to look a little bit more about this today. But if a particle and its corresponding antiparticle collide, we said that they totally 100% annihilate each other. They disappear. The matter that they were made of disappears, and their combined mass is converted into energy in form of gamma photons, which is pretty wild. Matter gets destroyed and turned into gamma photons. So let's check that out. I've got a proton and an antiproton collide, and 2 gamma photons are produced. We want to determine the frequency of the gamma photons, and we are going to, for simplicity's sake, ignore the initial kinetic energy of each particle. So they're coming together with essentially no kinetic energy. So first thing I would probably do is choose a physics principle. And you know what? I was just going to write physics principle. It's that kind of a morning, I guess. It's physics principle 6. So what is physics principle 6? It's our law of conservation of mass energy. We use physics principle 6 anytime mass is turning into energy or energy is turning into mass. So the way I write this out, mass energy, our total mass energy before, is equal to our total mass energy after. So let's see here. Before, I've got the mass of a proton and the mass of an antiproton. So that's going to be my mc squared, or delta mc squared, plus delta mc squared. So I'm going to put one of these as a proton and one of these, that's kind of hard to read, as an antiproton. And then on the other side of things, well, each of those turns into its own gamma photon. That's not at all what I wanted to write. Photon plus energy of a photon. But hold on, let's think about this for a split second. The mass of a proton and the mass of an antiproton. We just talked about how the properties are exactly the same except their charges are opposite. So if the masses are exactly the same and 100% of their mass comes from the mass of a proton, or which is equal to the mass of an antiproton, well, couldn't we just write, it's not supposed to be narrow, it's supposed to be a line, couldn't we just write 2 delta mc squared? Absolutely. And then these photons, well, if each proton and antiproton turns into a photon, those photons should have the same amount of energy. So it's 2 times the energy of a photon. Oh, look at that. You don't need those 2's necessarily. This is actually a little bit of an easier question. Delta mc squared is equal to, at least a lot less writing, is equal to the energy of one of the photons. Cool. Okay, so now all I really got to do is expand on the energy of a photon. So we know the energy of a photon is h times f, or hc divided by lambda. But the question is asking for frequency, so we might as well use the one with frequency. We got to remember with this Planck's constant, there's 2 versions. There's one that deals with electron volt seconds, and there's the other that deals with joule seconds. And whenever we're using delta mc squared, it needs to be joules. Needs to be joules. Okay, so the mass of a single proton or an antiproton, 1.67 times 10 to the negative 27, and we're using that whole entire mass because the whole thing is turning into photon energy, times the speed of light squared. Well, that's 3 times 10 to the power of 8 meters per second squared. That's going to be equal to Planck's constant 6 point. I got to double check this because we were just doing a bunch of gravity stuff with my physics 20s. Planck's constant 6.63 times 10 to the negative 34 joule seconds. I always get that confused with the physics 20, 6.67 for the gravitational constant. Not to confuse you right now, but 6.63 times 10 to the negative 34, and then that's times the frequency. So when we rearrange and solve for the frequency, and I'm doing this a little bit backwards than I usually do, but that's okay. When I rearrange and solve for the frequency, 6.63 times 10 to the negative 34 joule seconds. So get rid of that one. The frequency turns out to be, let's plug it into the old calculators there, 2.27 times 10 to the power of 23 hertz. Now thinking about that, that's a pretty high frequency, like a really ridiculously high frequency. Excuse me. Which means it's going to be really, really high energy. You're taking an entire proton and turning it into a gamma photon. Ridiculously high energy. Cool. So that's one thing to kind of check out. Next thing we want to talk about is the idea of quarks. So we said that there were hundreds of hadrons. That is no word of a lie. Scientists have discovered hundreds of hadrons, hundreds of different hadrons. So they started to think, well, maybe they can't all be elementary particles, right? No internal structure. So they started to dig a little bit deeper, and they discovered quarks, and they figured that all hadrons are composed of quarks. So they do have internal structure. They are not true elementary particles. So the quarks that we need to know about in Physics 30, we need to know up quarks, we need to know down quarks, and anti-up and anti-down, so they're corresponding antimatter. Now there's information about these quarks on the back of your data sheet. See if you can figure out where that information is in the back of your data sheet. So back is where I say you got all your constants, prefixes, particles, stuff like that. Look in particles, look in first generation fermions, and then down towards the bottom right-hand side, you've got up quark, anti-up quark, down quark, anti-down quark. Cool. So things that we look at with this, the up quark has a symbol of U and a charge of positive 2/3 of the elementary charge. That's right, less than the elementary charge. The down quark, negative 1/3 of the elementary charge. If I were looking at anti-up, well, it's going to have the same properties but opposite charge. It's going to be negative 2/3. Anti-down quark, positive 1/3. So just kind of things to keep in mind there. One thing to note is that there are other quarks that do exist. They're just not necessarily part of our curriculum. So there's the strange quark, the charm quark, the bottom or beauty, the top or truth quark. So you're getting into these, I like to think of them as like hippie names. I actually have no idea what they're named after. But typically in like the 60s is when people were discovering a lot of this stuff. So I like to think of them as just like cool hippies doing like peace signs and stuff. And then also doing some pretty high level physics and discovering quarks. So that's pretty cool. And then the other thing that we kind of talk about that's pretty neat with this is we don't call it like a type of quark, we call it a flavor of quark. So different flavors of quark, which is kind of neat. Getting into some different, more modern language, I suppose. All of these obviously have their corresponding antiparticles as well. So when we take a deeper look at protons, protons are actually composed of 3 quarks. There's 2 up quarks and 1 down quark. So it's up, down is what we're looking at. Cool. When we add that up, I've got 2/3 plus 2/3 minus 1/3. Well, that's, I guess I should do it this way, 3/3 or a charge of positive 1. Hey, that's a proton. Perfect. When I look at a neutron, also composed of 3 quarks, I got up, down, down. So there's positive 2/3 plus 1/3, or, you know, I could do it that way, I suppose, plus negative 1/3, which equals to 0/3, which is just a charge of 0. Perfect. So there's not no charges inside of a neutron. It's just the charges add up to 0, which is pretty cool. So real quickly, can you determine the charge of the pi meson? Another hadron, the pi meson. So there's an anti-up and a down. Go ahead, you can put it on pause if you need to. Try and figure out the charge of a pi meson. So let's see, an anti-up would be negative 2/3 plus a down, which is negative 1/3. So negative 2/3 plus negative 1/3 is negative 3/3, which is a charge of negative 1. So pi meson has a charge of negative 1. Pretty cool. Let's just check out this beta decay a little bit more. So we've talked about beta decay, we've talked about beta positive, we've talked about beta negative. There's the beta negative particle. I lost it for a second there. Let's really try and think this one through. So for beta negative decay, let's look at the thing over here. Which one's beta negative? That's this one. Is it when we have beta negative decay, we'll start with the easy thing, something you just got to remember. It kicks out an electron, so that's easy. It also kicks out, what's this one called? An antineutrino. So let's go back to this page. It kicks out an electron and an antineutrino. Now let's think a little bit harder about this. Oops, wrong way. Wrong way still. I'm going from radon or radium, I honestly don't know which. It's got an atomic mass of 228 and an atomic number of 88. Then I'm going to actinium that's got an atomic mass of 228. Cool. So the atomic mass didn't change. The total number of nucleons is the same, but look at this. I have 1 more proton, so an extra proton. So what that means is a neutron must have turned into a proton for beta negative decay. Cool, so a neutron turned into a proton. So let's just think about that. I had a neutron before, we said it was up, down, down, and it's turning into a proton. So as it turns into a proton, it must be up, up, down. So that means that a neutron turned into a proton, and where is it? We're going from a down quark to an up quark, which is kind of neat. And again, it's the weak nuclear force. It is the weak nuclear force that is responsible for the flavor of those quarks. Cool. If I look at beta positive decay, it's going to be pretty much opposites, but we can still go back and check it out here. So beta positive decay is this one. I've got a parent nucleus. Oh, this might be kind of hard to see, but see this one right in the middle here? That's the one that changed. So let's see. I'm kicking out a positron. I'm kicking out a regular neutrino. So let's start with those. So kicks out a positron, kicks out a regular neutrino. In this case, a beta positive decay, it's getting rid of a full positive charge. getting rid of that. So we're probably going to go with a proton into a neutron. Oops, plus to 0, right? And in doing so, kicks out that beta, oops, 0 and positive 1. Cool, so if it's going from a proton to a neutron, it's up, up, down, and it must be turning to up, down, down. Cool, okay, so let's see. Proton turns into a neutron, and it's turning from an up quark to a down quark is what we're looking at for that beta positive. So just explaining that a little tiny bit further. Now, evidence for quarks is pretty neat. So if a proton, and this is some of the first and some of the simplest evidence we actually see. So if a proton was a solid positive, just the whole thing was solid, the same thing, all positive, all no matter what, if you fired electrons at it, the electrons, no matter what, would be attracted to that proton. Turns out, through very, very, very careful observation and experiments, electrons are not always attracted to protons. So yeah, most electrons absolutely would be attracted and curve towards our protons, but every now and again you get an electron that is deflected away from a proton. Why would a negative electron ever be deflected away from a positive proton? Well, the only thing is, if it's got some internal structure and some of that internal structure is negative. That is some of the first and simplest evidence for quarks. Cool. So the standard model in Physics 30, you got to be familiar with this essentially, with what's on your data sheet. So, excuse me. Keep in mind, most of this is fairly straightforward. Your mass is a little tiny bit trickier in mega electron volts per speed of light squared. Remember, that's based off delta mc squared, and it's talking more about the energy. So if you go back to, I think that must have been lesson 1, you can figure out the energy in joules for that if you need to, but its mass is in terms of energy. When you see this, so for example, an up quark has a mass of approximately 5 mega electron volts per speed of light squared, and you're using question, just use 5. Right, just use 5. And I think there's actually, now that I'm thinking about it, I think there's actually a typo on this for the neutrinos. Yes, the neutrinos, where are they? Electron neutrino. So this is less than 50 regular electron volts, not mega electron volts, and then the antineutrino regular electron volts as well. Electron volts per speed of light squared, I should add. So keep in mind, little mistake on here, because they're so ridiculously tiny, like ridiculously tiny. And again, with that one, it says approximately 5, approximately 10, less than 50 for the neutrinos and antineutrinos. Just use the value that's on there when you're looking at any questions. Cool. Last thing we want to talk about here is just something that I think is really, really cool. CERN and the European Organization for Nuclear Research. So it is the world's largest physics lab. There are 20 European member states. I think this is really cool because this is just like, this is what science is all about. These places all in here, you know, they got their own issues and, you know, they squabble and they fight now and again and stuff like that. But they have together 2,600 full-time employees, and this is probably old stats too, as well as 7,900 scientists and engineers from around the world. They represent 500 universities and 80 nationalities, so 80 countries from around the world, which is pretty cool. It's all these people working together using CERN and the Large Hadron Collider and the particle accelerators to learn and to work together. I think that's just like so cool. So CERN itself is like massive. These are farmers' fields down here and like little spots of cities or something. I don't actually know, but it's massive, like kilometers and kilometers and kilometers across. We see tons of different synchrotrons as their particle accelerators. So starting off with smaller ones until it gets too big, then it goes into, or sorry, too fast, then it gets into bigger ones. The synchrotron speeds up, speeds up, speeds up, speeds up, and by the point it gets to the Large Hadron Collider, that's where we're going 99.999% the speed of light, which is pretty cool. Some photos of it. This is inside. This is some of the synchrotron magnets. You can see this radius of curvature. Like, this is just huge, absolutely huge, the radius of curvature there, which is pretty cool considering we're dealing with like the smallest stuff. We're dealing with the inside of protons, how big it is. Oftentimes, the smaller the stuff you're dealing with, the bigger the device is. This is the actual Atlas detector inside of the Large Hadron Collider. So this is where they actually detect the little particles. They smash them together. They see what comes out. This is how they see what comes out. This is a person standing right here. So again, absolutely massive. If this is a field trip I would love to go on one day. This is it, everybody. This is a little sad for me, but this is it. The last lesson of Physics 30 is now done. Congratulations, everybody. I'm super proud of you for hanging on, for going through, for doing not the easiest course, that's for sure, but hopefully one of the most entertaining and eye-opening courses in terms of sciencey stuff anyways. This, for our COVID-19 year, you don't really need to worry about too much. There's no diploma this year, and there's not really a last unit test. So, yeah, just make sure you studied up, you know what you need to do, and yeah, and if you need anything, just reach out, right? Even over summer, you can shoot me an email. Anyways, I'm happy that we're done, and I'm happy that you've stuck along and learned and done what you need to do. I'm really proud of you for that. I'm a little bit sad that we're done because, well, I don't get to hang out with you very much anymore. Anyways, we'll leave it there. I'll stop rambling about that. I'll talk to you again soon, everybody. Bye for now.